Hello and welcome to section 3.1 Extrema on the interval, and in this section we are going to talk about finding relative maximums, minimums, and also absolute maximum minimums, and so we'll kind of go through that as we go through this section. But first of all, for example 1 here, they want us to find the value of the derivative of the relative extrema for each one of these. So the first one is this function right here. And we want to find the relative maximum. What's happening with the derivative at the relative maximum? And so in this one, by the time we're done with this example, you should have a pretty good idea of what's happening at the derivative when we take to the derivative when we're taking when we have a relative maximum minimum. So when you walk away, you should say, oh, if I take the derivative and do this, then I should be able to I should find either a maximum or minimum. So. And you may already know, but we'll start with A. And so it says f of x is 9 times x squared minus 3 all over x cubed. Well, because there is an x on the top and on the bottom, and there's really no way I can divide this out and make it nice and neat, I'm just going to do a quotient rule on this. And so when I'm talking f prime of x, I will take the 9 is just a constant multiple, so I'm just going to leave it in the problem. And so when I do this, I would say, okay, well, the derivative of the top would make me get 18x, because that's the multiplication of this, times the bottom, which is x cubed. Subtracting, leave the top alone, and then take the derivative of the bottom all over the bottom squared, which I'm going to square x cubed and just make it x to the 6th right away to save myself a little bit of a step. And so then if I go ahead and do a little simplification on this, you'll notice I have 18x to the 4th minus 9 times, well, I'm actually going to multiply all this out just to make my life a little bit easier. So I'm going to go 27x to the 4th, and then we have 9 times 9, which is plus 81 x squared all over x to the 6th, because when I squared that. So then what ends up happening is if I go, okay, if I do a little simplification, first of all I can combine these guys together, get negative 9 x to the 4th, and then I could also get rid of an x squared top and bottom. So I'm going to do a little bit of factoring here and say, okay, well, f prime of x is, this becomes negative 9 times, and I have x to the 4th plus, oh, nope, it becomes minus. I'm probably doing too many steps, so let's back up here. So if I combine these, I get negative 9 x to the 4th plus 81 x squared all over x to the 6th. And so you may notice that I've got a 9 in common on the top, and on the bottom here I have x to the 6th. So I'm just going to kind of move over here to save myself some room. So f prime of x is going to be, if I factor out a negative 9, I'm going to factor out a negative 9 x squared. Negative 9 x squared. And then I'm left with x squared minus 9 on top all over x to the 6th. And so then if I go ahead and divide out the x squareds, I'm left with f prime of x is negative 9 times x squared minus 9 all over x to the 4th. And so I have this as my answer. And so now if I plug in my x value for my maximum, plug in my x value for my maximum, f prime at 2, or at 3, sorry, my x value, and I will find out something about this. So negative 9, and then I get 9 minus 9 over x to the 4th, which is 3 to the 4th. And so plugging this in, I get 0. It looks like I get 0 on top. I get 9 minus 9, which is 0. And 0 times negative 9 is 0. So 0 over any number, as long as the bottom is not 0, is 0. So when we take the derivative at a maximum, we end up with 0. So then for part B, I'm going to find the relative minimum of the absolute value function. And so if I go ahead and do that, I'm going to say, okay, well, f of x equals the absolute value of x, and we don't have a derivative function for the absolute value of x yet, so I have to do the limits from the left and the right. So the limits as x approaches 0 from the left and the limit as x approaches 0 from the right could be written as f of x minus f of 0 all over x minus 0, just using our standard difference quotient. And so then this one, f of x minus f of 0 again all over x minus 0, and plugging in the values for f of 0, which is 0, gives me basically a function where we're doing the limit as x approaches 0 from the negative side. From the negative side, it's supposed to be an arrow, from the negative side, that we get the absolute value of x over x. And so when basically what I can see is as I'm approaching 0 from the left-hand side, I get a slope of -1. Also, on the right-hand side, as we approach from the positives, you can see we end up with the same function, but this time, when I plug in my value from the positive sides, I get +1, and so I have these two different slopes, and so we have at f of 0, f prime of 0 does not exist. Alright, so that's also a thing that can happen when we're talking about a relative maximum or minimum. When we take the derivative, it cannot exist. So then we have our final function, and I'm just going to get rid of this right here. Actually, I'll just move these guys down. We have our final function, and we'll talk about these graphs in just a second. In our final function, it's the sine of x at these points, and so I just want to have pictures for you. So for the final one, it's c, it's f of x is sine of x. And I believe we want to do it at pi over 2 and 1, and 3 pi over 2 at -1. So we take our derivative, which is f prime of x, which gives us cosine of x, and so then we're basically plugging in pi into x, and so f prime of pi over 2 into cosine of x will give me 0. That's just from my unit circle. And the same thing happens if I do f prime of 3 pi over 2 in for x. We get cosine of 3 pi over 2, we get 0. So at this, we get our relative maximums and minimums to be 0. So if we're looking at our graphs, you can see what's happening when we ask for the derivative. We're asking for the slope. And so what we're finding is that when we take the derivative of the function at a maximum or a minimum, we either get a 0 slope, which is a horizontal line, or we get a no slope at all, and undefined. And so that's really what we need to walk away from this problem and know. So in the next section, in the next one, we're asking you to find the extrema. So we're just looking for maximums and minimums. And since it's on a closed interval, that means we're going to include these points. So to find the extrema, so from the previous one, we said we can find maximums and minimums by setting the derivative equal to 0. And when the derivative is 0, as long as there's no sharp points or it does not exist, set it equal to 0 or set it equal to does not exist, we can actually go ahead and find that there's a max or a min there. So basically what I'm going to do is I'm going to take the derivative of this function, f prime of x, and when I take the derivative, I get 12x cubed minus 12x squared. And so if I set this function equal to 0, I will find out values of x where they have a maximum or a minimum. And to make my life a little bit easier, I can do some factoring. You'll notice I have a 12 and an x squared in common. So if I do that, I get x minus 1, I believe, when I factor. So I have these guys. So now I set the derivative equal to 0, because we just said in example 1 that if we set this guy equal to 0, we can find relative maximums and minimums. So you can see that we have either a maximum or a minimum, possible maximum minimum at x equals 0 for the 12x squared equals 0, and we have another relative maximum or minimum possibility at 1. So now if we want to find out what the maximum or minimum are, we're going to use these are what we call critical numbers. And so these critical numbers, and we'll talk about this a lot, these critical numbers are very important. These are, like I said, where maximum minimums appear, relative maximum minimums, but we want to find absolute, we want to find all the extrema, so we're going to also include our endpoints. So I need to find out what f of -1 is, and this is the original function f of 0 f of 1 and f of 2. And so we just do this, and when we plug these guys into the original function, the largest value will be the maximum, the smallest value will be the minimum. And so it may be endpoints, it may not, it just kind of depends on the picture that we're looking at. And if you want to see what the picture looks like, I would go ahead and graph this and set your x values to this, and it'll set your x window to this, and you'll see exactly like where it starts and where it ends, and you can kind of pick out these. So if I put -1 into this function, looks like I get 3 -1 to the 4th minus 4 times -1 to the 3rd, which means I get a +3 and a +4. So 7 is my value for that one. If I put 0 in, I'm going to get 0. If I put 1 in, I'm going to get 3 take away 4, which is -1. And if I put 2 in, well, I'm going to get 3 times 16 minus 4 times 8. So this ends up being, when it's all said and done, I believe gets me 16. So I have my maximum. This is an absolute max. Absolute max at 16, and in this, because it's a closed interval, we can call them absolute. And this is a minimum, an absolute minimum at -1. Now we don't have to worry so much about absolute and relative. They just, when we have a closed interval, we are concerned with the endpoints also. And that's the key to this. So in the next example, we have a little bit trickier function, and again I would graph this to kind of get a picture of what you're looking at so you can see what it is, and set your x window to these values so that you can kind of hone it in on what exactly we're dealing with. So again, if we're asked to find extrema, we're going to take the derivative and set it equal to 0, and so this guy we end up with 2 minus, and then when I take the derivative I get 3 times 2/3 x, and when I reduce that by 1, I believe I get -1/3, which makes this a little bit different type of function for us, because we end up with, it makes it a little bit harder for me to set equal to 0. So what I'm going to do, let's see, we'll just do a little simplification of this. I get 2 minus 2 x to the -1/3. And so what I have to do is get a common denominator to make my life a little bit easier. And so I'm going to multiply this 2 over here, this 2, by x to the 1/3 power, top and bottom, so that we can end up with, because this guy's supposed to be on the bottom, and so we can end up with the same thing. So I really have 2 x to the 1/3 minus 2 over x to the 1/3. I was just getting a common denominator by multiplying this by the fraction of x to the 1/3 top and bottom, because this guy was already going to be on the bottom. And so now, at this point, since I have this as my function, I can set it equal to 0, and you'll notice that when I set this equal to 0, that the x to the 1/3 on the bottom, when multiplied across to get rid of the division, will go away. So really I only have to concern myself with the top when I'm looking for maximums and minimums, setting the top equal to 0. So when I set the top equal to 0, I have 2x to the 1/3 minus 2, and so then I add my 2 across the equal sign. So let's see, we get 2x to the 1/3 equals +2, divide by 2. So I get x to the 1/3 equals 1, and so in order to get rid of a 1/3, I'm going to cube both sides, take it to a power of 3, which basically means x is 1. And so in this guy, I have my maximums of 1, and let's see, I'm trying to think if there's any others. So then I've got -1 and 3, and I could also have, in this case, I could also have had 0, because that's where the bottom would equal. That's where the bottom could equal a function that doesn't work, and so I'm going to go ahead and say 0 is a possibility also, because 0 would make this not work, the original function, make this function, the derivative, not work. So I'm going to use that too, even though I said it's going to multiply out of it. We're just going to say, okay, this guy is also going to be included when x equals 0. So now I have f of -1, f of 0, f of 1, which 0 and 1 are my critical numbers, and then f of 3, which are my endpoints on my closed interval. So plugging these guys back into the original function will give me the highest and lowest y value. Well, plugging negative 1 into the original function, I will get negative 5. Plugging 0 into the original function, I will get 0. Plugging in 1 into the original function, I'll get negative 1. And plugging 3 into this function, I end up with, let's see, 6 minus the cube root 3 times the cube root of 9, which is approximately negative 0.24. And so just do the math, plug it in, and you'll see what you'll get. You should get these numbers. So these being my endpoints, then this basically means that this right here is my minimum. Negative 1, which is one of my endpoints, is a minimum, and my maximum is actually at 0 here. And so we need to make sure that when we're setting both the top and the bottom, and I apologize for making that mistake a little bit ago. So then finally we have this one, and we're trying to find the extrema on this one, and you should graph this function and set it to this interval so you can see what it looks like in your x-axis. Set your x window to this so you can see it. So I'm going to go ahead and take the derivative of this function. And when I take the derivative of this function, this sine x, it just goes to 2 cosine x, no big deal there. And then this one over here, when I take the derivative of it, remember it's going to take a chain rule. So I take the derivative of the outside, so cosine goes to negative sine, so it really turns into positive sine of 2x, and then I got to multiply by the derivative of 2x, which gives me 2. So it's really 2 sine of 2x. So now, at this point, I'm going to say 2 cosine x plus 2 sine 2x is going to be what we're going to set equal to 0. Well, the issue with this is that we don't like having a double angle and a single angle, so I'm going to actually use my double angle formula for sine, one of them, and say sine of 2x could be turned into, to get rid of it, and this is something you guys need to know, is the double angle formula is this formula. So this is the original 2 that's there. The formula is 2 sine of x cosine of x. And that's our double angle formula, and that will help us along the way. So I'm going to multiply these 2's together, which gives me 2 cosine x plus 4 sine x cosine x. And the reason we would do this is it just makes my life a little bit easier, that if I factor out a 2 cosine x, so 0 equals 2 cosine x times, and this is just going back to our zero product property of when we were in algebra 2, that we can factor these guys out, and now if I set each one of these equal to 0, I can find my critical numbers in this function. And so I want to change colors there, 2 cosine x equals 0, and 1 plus 2 sine of x equals 0. So we just set them apart and solve. Well, dividing by 2 over here for cosine, it just means where's cosine equal to 0, and so that means my x is at pi over 2, or 3 pi over 2, in this interval. And so then, if I solve this one, if I solve sine of x, I subtract 1 and divide by 2, so I really have where is sine of x equal to negative 1/2, and so that puts me at, in this interval, that puts me at 7 pi over 6. X would be 7 pi over 6, and also 11 pi over 6. And because, remember, sine is the y value when we're dealing with this, and it's at the bottom, has to be in the third and fourth quadrant to get a negative, and that's where the sine is negative 1/2. So now, if we're trying to find the relative extrema on this, we're going to go through and plug these guys in, all of our, so we've got 4 plus these 2, so we got 6 that we got to find out which is the highest and which is the lowest. So we're going to do f of 0, f of pi over 2, f of 7 pi over 6, f of 3 pi over 2, f of 11 pi over 6, and f of 2 pi. And so I'm going to kind of leave those calculations to you when you plug them in, just for sake of time, but we'll get the numbers for you. If I put in 0, if I put 0 into the original function, you'll see that I'll get -1. If I put in pi over 2, you can go ahead and calculate it with the original function and get 3. If I put in 7 pi over 6, I'm going to get -3 over 2. If I put 3 pi over 2 into the original function, I get -1. If I put 11 pi over 6, I get -3 pi over 2. And the last one, if I put pi over 2, I get -1. So the question is, what are our maximums and minimums? Well, you should be able to see our maximum is the 3, because that's our largest value. And then our minimums are going to be our smallest numbers, and that's the -1.5. And so we have 2 minimums, and you can have more than one maximum or minimum as long as they're the same values when we're talking about these. So that concludes this section. Remember, if you have any questions, come to class and be prepared to ask them, and we will talk about this. Thank you.